All right, so what we'll do here is we'll have a brief overview of the code requirements and what you need to think about if you're trying to port the code to your own machine. And we'll actually compile the code and we'll do a very quick simulation and check on some of the numbers reported by Rayleigh. Before we begin, all exercises will take place in the desktop/Rayleigh tutorial folder, which should be there in your virtual machine. Within the Rayleigh tutorial folder, go ahead and create a subdirectory named module1. So that's where we'll put our first run in just a minute. So you should be able to cd to capital desktop/Rayleigh_tutorial. Yeah, you should see sample run 2, and we'll get there at the end. But for now, just make a directory called module1, mkdir. I think everybody probably knows that. And then really quickly, I'll kind of just go over the code requirements for Rayleigh are pretty basic. Okay, you need a compiler that supports Fortran 2003, which every compiler I've used GNU, Intel, and the IBM compilers. They all seem to do that now. You need a C++ compiler because Rayleigh creates some directories when it runs, and we have a C++ routine that handles that. Fortran has some issues doing that. You need BLAS and LAPACK, which are pretty standard if you're doing any kind of scientific computing. You need FFTW3 or later, and then MPI. Okay, that's really all you need. You don't need HDF5 or anything like that. Rayleigh's outputs are done in unformatted binary, and I have some Python routines to read those in, which we'll cover later. Okay, so the first thing we're going to do now that you've made the module 1 directory is change over into the directory called Rayleigh. Okay, and all we're going to do is we're going to execute this command. Okay, we're going to say /build_Rayleigh.bsh space and then all caps CIG. Okay, and we'll talk about what this is doing in just a minute. But what I want to do first is just make sure everyone actually sees the thing compile when you do that. So if you build it, you should see something like this scroll across the screen. Did anybody not see that? So I'll let mine build so that I have a working copy. Then we'll talk about what just happened here in just a moment. Okay, so if you look in the build directory, which you can see things laid out by their timestamp if you do ls-ltr, the last thing you should see, so ls-ltr space build, the last thing you should see is the Rayleigh executable. Okay, so it places the executable in the directory called build, and so that's where we'll grab a copy. Typically what I do is I soft link Rayleigh to the run directory, which I'll go over that in a minute. But that's where it puts Rayleigh when it builds it. Okay. All right. So what's going on here? When we execute this command, there's various subdirectories in the Rayleigh directory that pertain to different portions of the code. It just copies all the source files from those to build. It copies a make file with the same tag that we gave it, which was CIG, over to build, and then it just changes, the script just changes into the directory and builds Rayleigh. You'll notice there's another file called ./build_Rayleigh without a BSH. So for whatever reason, Ubuntu doesn't come with C shell installed by default. Most machines, other machines do, so you can also use the build Rayleigh script as long as there's a CSH application installed. Okay. So typically, if you want to port to a new machine, what you're going to do is you're going to take one of the make files in the make files directory, and we'll look there in just a second, and you will make a copy of it and modify it, and you'll give it some suffix. Okay, and then when you want to build it, you just pass that name that you gave your make file to the build script. And so there's some examples in here, kind of the three important ones. If you look, there's an Intel compiler example for Pleiades. There's an IBM compiler example for Mira, and then there's a GNU compiler example, which we just did. So if you look in the makefiles directory, you should see there's several of these things. Okay. A lot of these are redundant. They're just from different machines that I was working on that had, they're basically Intel machines with slightly different paths for the MKL libraries, etc. So if you were to look at one of those, which you can, you might look at makefile CIG. You'll see a few things which are really all you need to think about if you're trying to move this to your own machine. There are these compiler-specific flags, you know, -03. Are we doing debugging? This is a GNU example. The line length needs to usually be 132 spaces. You need to think about the include directories. And then you need to think about how to link your libraries, BLAS, LAPACK, and FFTW. Okay? And that's done differently depending on what sort of architecture you're on, so, or in what sort of compiler you're using. So what I do is I typically take one of these three examples and modify them when I port to a new machine. The other thing, you can call this with an additional option, which is then passed to the makefile. And so if you look at the makefile CIG, you see there's a little if-else construct here. And so if you pass a debug option, it will compile with debugging flags. And so we can try that. So after CIG, when you build it, you can build with debug. This is useful if you're making some modifications to the code. This turns on, you know, the normal debugging flags, checks the bounds of these arrays, that kind of stuff. Has traceback so you can see where things crashed. But you can try that and just convince yourself that this also builds, but then build the code back to its normal state, right? So build Rayleigh, CIG, debug, and it compiles with a different set of flags. But for now, we're not going to debug. We want it running as fast as it will run, so compile it again without the debugging, because we're on a pretty limited system here. Okay, so please just rerun the other command and make sure it compiles with -03 and you don't see fbounds check or anything like that. And then once that's done, change over to this directory, this module1 directory that you created. By the way, I want to make a quick comment. PowerPoint recognizes Rayleigh as a proper name. The only time Rayleigh is capitalized in this is in Rayleigh tutorial. You will see occasionally other Rayleighs capitalized. That's PowerPoint trying to thwart this tutorial, okay? So don't capitalize it. All right, so what we'll do, so typically when you run the code, what you do is you have a directory where you're going to do a particular simulation. Okay, so we make unique directories for each simulation that we do. Okay, so we'll change to this module1 directory. And then what we're going to do is we're going to soft link the code. Okay, you can also copy it if you want to, but I soft link. So soft linking, I don't know if everyone knows, but it's kind of like, it's like your desktop icon. Okay, you can delete the soft link, but you don't delete what it points to. This way, if you're doing some development, you just recompile the code and you don't have to remember to copy the executable. You have a soft link that points to it. So this is just ln-s /Rayleigh/build/Rayleigh, and then dot tells it to link it to where you are. So I'll do that too. So So module 1. And once you do that, do a little ls. Okay? If it worked correctly, you should see, actually I'm not sure what color it does it in Ubuntu, but if it works incorrectly, like I did here with test, you'll see it highlighted in some kind of ugly coloring. Okay, so if you mistype something, you'll see this, but otherwise you'll see this very light colored, probably be blue or green thing. Did anyone have any issue doing that? Okay, so I'll remove test. Okay, the next thing we need to do, we need to grab an input file. So Rayleigh, basically you need two things in your directory. You need the code and you need an input file. And so there's several input examples, which we'll talk about in a bit, and they're located in the Rayleigh/input examples directory. And so what we want to do right now is we want to grab this one input file called C2001 case 0 underscore minimal. Copy that into your module 1 directory. And then what Rayleigh wants is it wants this input file to be named main input. So once you copy it over, go ahead and move it to main input. Rayleigh doesn't look for C2001 case 0. And then once you've got it there, open up main input in a text editor and we'll look at it. Okay. I like get it. I know people like VI or Emacs, what have you. Okay, but if you were to open it up with get it, this is what you'd see. So the way Rayleigh works is the input file has a series of name lists, and each name list controls some piece of how the code runs. Rayleigh has a lot of defaults set internally, so you could effectively have an empty set of name lists and it would do something. I don't even know what it does if you don't set anything. But several things have default values that we'll cover during the course of this tutorial, so there's things that you often don't need to set. For instance, Chebyshev is the default mode of the code now. We could just delete that line if we wanted to. But the idea is whatever you set here overrides whatever default is set in the code. Okay, so this is how we pass Rayleigh instructions, and really we're going to be working our way down through these name lists throughout this tutorial. Okay. So for now, let's change these 6 values in our main input file and save it. Okay, so if you kind of scroll down, what we're going to do, we're going to change the resolution to something a little bit lower than this so that it runs quickly. We're going to change the process layout, and that's covered more in the next section. And then change the number next to benchmark report interval so that it's 500, and then change the max iterations to 2500, and then save. Okay, so to run the code within your module 1 directory, what you do is you type mpi exec space -np4, which tells it 4 processors, /Rayleigh. Okay? And I'll get that going on mine too. So What you should have seen when it started, if you scroll back up, you should see kind of a preamble that tells you something about the run settings. Okay, and this isn't all-inclusive, but it tells you a lot of the important things. Okay, it tells you how many CPUs you're using. It tells you how many are in a process row and a process column, which are those lines we changed. It tells you something about the resolution. And then, if you look, you should have seen a little report indicating that you were running one of the benchmark cases. Okay, and so what are these? All right. So what are we actually doing? There are a couple of papers out there that are very useful for testing codes like these. Okay, they handle, they examine rotating convection in a spherical shell, but they have very simple solutions. And so the idea was that several people brought their codes to these benchmarking exercises. People ran things and saw how well codes agreed, and most of them agreed pretty well. Out to usually the things we measure various aspects of these simulations. Things agree to like 4 or 5 digits typically. But the idea is that these are fully nonlinear simulations, but they're very low Reynolds number. And what you tend to get are these sort of convection that is really dominated by a sectoral mode. And it's steady, except that the pattern is drifting in the rotating frame. Okay, and so what you do in these exercises are you measure the drift rate of the pattern, you measure the temperature and the magnetic field and the zonal velocity at different points on the pattern. You measure the kinetic energy of the simulation, you measure the magnetic energy of the simulation. And if you've ever done one of these, you know it's kind of a pain to actually carry out these analyses. So what I did is I built this into Rayleigh. Okay, so this is all done in the code. And what it will do when this is finished is it will generate a little report for us. And I use this all the time when I move to a new machine. I run typically one of the Busanesque benchmarks like the one we're running right now because it's cheap and it's extremely quick. The Jones et al., this Icarus paper, are anelastic benchmarks, but these inputs are the Busanesque inputs. So but for both of these, they have effectively the solution has this character, and there's an MHD version and a Hydra version, and there's an anelastic and a Busanesque set you can run. Okay. So whenever you're porting to a new machine or testing this out somewhere, run this one that we're doing right now at least. It's cheap and quick. Rayleigh input C 2001 case 0 minimal dot gedit. Yeah, so the one you used probably looked like this. Okay, so what happens is this benchmark mode equals 1 will fill all this stuff in. The other one that's just called input and not minimal, it actually shows you how you would set this run up if you wanted to, and then you can modify the parameters. But basically, it's down here, and then the init type 1 tells it you set up this like a particular spherical harmonic mode and temperature with a conductive background state. Yeah. Okay. All right. So if everyone's done, if you just do an ls, you should see that Rayleigh created a series of directories. And then if you look in benchmark reports, you should see a few files with numbers. If you look at one of these, in fact, look at the last one if you have it, the 2500. Okay, it gives you some information. Okay, it tells you which benchmark was being run. It tells you the run resolution. It tells you, in this case, the different time steps that went into building this report, how many samples were taken. So we were taking 1 sample every 100 time steps. And it tells you the actual averaging interval in the simulation. So this is a tiny averaging interval we've taken. And then it tells you some things about the measurements that were being made. Okay. And so in this case, we were measuring the kinetic energy of the simulation, and we were doing point-wise measurements of temperature and V phi, and then we're measuring the drift rate of this convective pattern. Okay, and then it tells you what you measured. It tells you what's suggested. Okay, and then it gives you a percent difference. All right, that's important too. This really is a percent difference, so it's the relative multiplied by 100. And then it tells you something about the standard deviation of these different quantities over this averaging interval. Okay, so the idea is that these things reach a steady state, and so that standard deviation, if we were to run this long enough, would go down and down and down until it would basically be 0, 0, 0, 0, 1. So if you look at your 2500 example, okay, and then you'll notice one level back in the tutorial directory there's a file called accuracy check. If you compare those two files, if your code is functioning correctly, they should look the same. And I think you can't do a diff on them for some reason. Some machines you can and some you can't. They're just text, but some machines don't. I'm not sure what's going on there, but you have to do more. Okay.
This is accuracy check is not in the benchmark.
Accuracy check is one level back in the Rayleigh tutorial directory.
It's in module 1.
No, it's one level back from module 1. Does anyone have the file 2500 and it does not match accuracy check? That's all I want to know here. Okay. So what accuracy check is I ran this on another machine and I ran the full benchmark out to equilibration, but I just saved and I got the right answer, but I saved a result from partway through so that we could check here in the tutorial. Okay. Okay. So are there any questions? The rest of this should go a little faster, but this is kind of the general mechanics. We pull an input file over. When you port it, you always want to do one of these benchmarks. And then we're going to start talking about how to actually control what the run is doing now. One single file is read by all of the processors. And eventually I'm going to have it so that one process reads that and broadcasts to everyone, but they all read main input. And then if you actually take these input files, we halved the resolution here. So if you ran with the resolution that was originally there and you ran this for about 30,000 time steps, you should see this thing converge. Okay.